In this video, I'm going to talk about hybridization, so orbital hybridization, which is used for bonding theory. And the next few videos, well, I mean, this is probably going to be like its own separate playlist. I'm going to be talking about molecular orbital theory. And hybridization is one of those things you learn it in general chemistry, and its terminology gets used a lot. Things, like sp2 bonds and sp3 bonds and things like that. But both my inorganic chemistry textbook and my advanced organic chemistry textbook say that it's somewhat obsolete, that uh, it's been sort of supplanted by molecular orbital theory. Although, like I said, it's the terminology still gets used a lot. And when you get into molecular orbital theory, there is orbital mixing and things like that. And so, there's maybe some room to say that hybridization is actually happening. So I think as my advanced organic chemistry textbooks say, that, this is stuff that's not actually happening. It's just sort of a tool to help us think about it and, sort of picture the geometry and symmetry of all this. But anyway, so I'm actually going to briefly talk about hybridization and sort of use the sort of symmetry group theory that I've talked about at length in my group theory lecture series. And so, I think it's kind of important to sort of show this stuff, even if, some people seem to think that hybridization theory is somewhat obsolete. But anyway, like I said, I will be going through this here. And so we will first look at, oh, and by the way, I'm kind of assuming that you already have at least a general chemistry understanding of hybridization theory. And if not, I do have a very brief general chemistry playlist, and you can sort of orient yourself using that. I do have a video that is about hybridization. But anyway, let's get into this. So if we have a tetrahedral molecule, which would be something like methane, then it has this tetrahedral point group symmetry. And so it's a molecule that looks like this. And so we have these bonds sticking off, forming this sort of tetrahedral shape like we have here. And I believe there is a 109.5 degree angle between each of these bonds. And so the tetrahedral point group is this character table right here. And we'll actually see here in a little bit that this character table could simplify things even more for us. But in this first example, we will go through kind of the whole process here. So we find the 4x4 matrices of the regular representation. So a regular representation, as I talked about in my group theory playlist, is one where we have these matrices where each column has only a single one in them, and everything else is a zero in the column. And so we can see that in each of these, each column of the matrix has just a single one in it. And so we have the identity element here, which is just one to the diagonal. We have the C3 rotation, the C2 rotation, the S4 inversion, and the sigma D reflection. And so if we just take the trace of each of these matrices, we get these characters right here. And so we have this as our reducible representation. So the trace of the identity is 4, the trace of the C3 is 1, the C2 is 0, S4 is 0, and the sigma D is 2. And so we can use this formula right here, which I covered in my group theory videos, to find sort of how many of these representations show up here in our group. And so we go through this formula for each one. So we look at the A1, A2, the E, the T1, and the T2. So we're looking at each of these right here, and we're sort of finding out how many of those exist using this reducible representation right here. And so we find that only the A1 and the T2 exist in this. So we have the A1 plus T2. And so this gives us the atomic orbitals with these symmetries. So the A1 and the T2. So we're just taking these right from the character table here. So the A1 here and then the T2 right here. And so that's what we're looking at here. And so this is associated with the S orbital here. These ones here are associated with the px, py, and pz. These ones with these 3d orbitals here. And so now that, so we see here that we have these sort of two options right here. So our hybridization could be happening with these p orbitals or with these d orbitals. And so it's saying that our hybridization could either be, sp3 or it could be d3s hybridization, depending on which one of these we use. And so to determine that, we have to sort of take energy considerations into account. And so for period 2 atoms, which is the second row on the periodic table, the one below the row that is just hydrogen and helium. So that would be something like methane or this ammonium. The s and the pn orbitals are closer in energy and would be much more likely to produce the sp3 hybridization. And for the period 3 atoms, which can contain things like the manganese and the chromium here, the 3d and 4s orbitals are closer in energy, and so for those we are more likely to have a d3s hybridization. So like I said, so since the character tables give us the basis in the irreducible representation, we don't have to calculate the n gamma for each irreducible representation. So we know that we only have to look at the ones that actually have things here in the basis columns. So we don't have to calculate that for all of them. So yeah, right here we can look at this. So we have the d orbitals here, so the dyz, the dxy, and the dxz. And I'll show here in a little bit sort of, well actually I'll show how those can form pi orbitals, but that'll be later on in the video. And so we only have to look at this. And so the thing to notice too is that this is in parentheses, which is because that is sort of a triply degenerate system right there, and because that sort of corresponds with all 3 of these d orbitals or all 3 of these p orbitals. So even though we only have one of these present here, so we don't have anything other than a 1 in front of the T2 there, we still have sort of 3 orbitals that are associated with it. And so if we look at a D3H point group, which is a trigonal planar molecule such as boron trichloride, we have this character table. And so we can find the reducible representation from our regular representation matrices here. And so this would be the reducible representation that we find. And so we only need to calculate the following because we only need to look at the ones that have stuff in the irreducible representation in those basis columns there. So we find that we only have the A1 prime and the E prime. And so the primes, by the way, I think I neglected to mention this because it's sort of used somewhat inconsistently, but the primes just mean if it's single prime, then it is symmetrical with the sigma h, and if it's double prime, then it is anti-symmetrical with the sigma h. But anyway, so we have the A1 prime and the E prime, and so the A1 prime has these 2 possible bases here, and the E prime has these 2 possible bases here. So molecules like the boron trifluoride and boron trichloride are likely to be sp2 hybridized, so using this right here and then these 2 right here, where molecules like this titanium three, well, actually this would be what, titanium, so what is the oxidation on this? So we have three oxygens here, so that would give us 6 minus, but we have this 2 minus here, so I believe that would be titanium 4 oxide. And so molecules like titanium 4 oxide are likely to have some contribution from the d orbitals, so possibly these ones here, possibly this one right here. So notice that the p orbitals used are only the px and the py, which are in the plane of the trigonal planar molecule. So we have this trigonal planar here, and so only the px and py, which are sort of in this plane here, will get used for the hybridization. The pz, which would be sort of sticking up and below the plane like that, are not going to get used in the sp2 hybridization. And we'll actually see in a little bit here that that can then be used in pi bond formation for double bonds. And so, yeah, these are the orbitals right here. And so we see the pz is sticking up above and below the plane, where the px and the py are in the plane. And so we see up here that we also have the dx squared minus y squared and the dxy, and so those are in the plane as well. So the dx squared minus y squared and the dxy here are both in the plane, and that's why those are possibilities for being used in the hybridization here, because those would be in the plane of these bonds in our trigonal planar molecule. And so that's why either the px and py or this dx squared minus y squared or this dxy will be used in the hybridization going on here. So this dz squared here is sticking above and below the plane, and so that is not likely to be used in our hybridization here. So then we can compare the square pyramidal and the trigonal bipyramidal point groups here, which are going to have the same number of bonds. They're just going to have different geometry. And so we can sort of compare these two here. And so I have the two character tables shown right here. And so we get the following two reducible representations. Oh, by the way, this is what those look like. So this is the trigonal bipyramidal, and it's trigonal because we see we have 3 bonds in the equatorial part of the molecule, and it's bipyramidal because these form sort of 2 pyramids on top of each other like this, and so that is why it's called trigonal bipyramidal. And this is the square pyramidal because we see this forms a square, and then if we drew a line from this going down to there, we sort of get a pyramid that has a square base to it. And so we have the trigonal bipyramidal, which gives us these orbitals here, and the square pyramidal, which gives us these bases right here. So if we sort of go through the same process as we did above, and so if we look at this, so the trigonal bipyramidal, the D3H has these two A1 prime, bases right here, which has both the S and the DZ squared orbitals involved, meaning that hybridization will have contributions from both of these. The PZ in the A2 double prime representation and the DZ squared in the A1 representation form the 2 bonds along the Z axis. So that would be these axial bonds. So this one right here and this one right here. So because the PZ and the DZ squared are both sticking up and down in the Z direction, those will form those two bonds along the z-axis. The E representation is likely to use the px and py for energy reasons. Therefore, the hybridization is likely dsp3. And so we are getting the D from here, the S from there, and then these two p orbitals right here, and then this p orbital right there. So for the square pyramidal, which is the C4V, we have the 2A1, but the S and PZ can either one of those can be used, with the latter for the single bond in the Z axis. And so it will, however, have a contribution from this dx squared y squared minus y squared orbital. The E representation is likely to use the px and py for energy reasons, and therefore we are most likely to again have this dsp3 hybridization. All right, so now if we get into the pi bonds here, which give us the double bonds. So this is what the pi bonds look like. So they're sort of they above and below the sort of sigma bond here, with a node here in the middle where the sigma bond is. And we can form up to two of these, which looks like this. So sort of perpendicular to each other in that fashion right there. And so if we first look at the trigonal planar molecule, the axes perpendicular to the sigma bonds in each of the 3B atoms. And so we're looking at A, B sub N sort of molecules here, where we have this central A atom, and then these B atoms sort of bound to that central atom there. And so here we would have an atom right there bound to three atoms on these planes right there. So in the plane here, forming this trigonal planar molecule. So the axes perpendicular to the sigma bonds in each of the three B atoms are either perpendicular to the plane, which would be these Z axes here, or parallel to the plane, which would be these sort of X, Y axes right here. So this is the D3H point group. And if we find the character of the perpendicular and the parallel ones, we get these two right here, and then we can just add those together, and we get this for the pi bond reducible representation. So after the reduction formula, we get this for the perpendicular and this for the parallel. And so these will be our bases right here, which come from that D3H character table. So we have this E prime here, and this 2A, 2 double prime, and this E double prime, where this 2A1 prime here doesn't have anything in it. And so the three perpendicular pi bonds can be formed with the PZ, the DXZ, or the DYZ orbitals. And so this comes from, so we can have either these two right here, or we can have these two right here forming the pi bonds. And so this is kind of what pi bond formation looks like, where we have these Z orbitals here, which can have this overlap between the two sort of, well, the two functions there that have the same sign. So if we say that that these white ones here have the negative sign and the blue ones here have the positive sign, like that. They can also form pi bonds with p orbitals, but that would look more like this. And so that's how we can have d and p orbitals sort of involved in pi bonds. So the three perpendicular ones could be formed with either the PZ and the DXZ, or the DYZ. And so the perpendicular ones are these Z-axis orbitals, and so they're the ones that have to be sort of sticking above and below the plane like that, where the parallel ones will be the ones that sort of stick sort of this way, sort of in the plane, but not involved in the sigma bonds. However, the sp2 hybridization for these sigma bonds in a trigonal planar molecule use the px and the py orbitals. And so only the dx squared minus y squared and dxy orbitals can be used for the parallel pi bonds. So we're saying that these ones here are already being used in the sp2 hybridization, and so we have to be using these orbitals right there. Uh, so, uh, so yeah, um, yeah. So the pi bonds formed by either the pxy or the px or the py, or these uh, are the only ones which can form the two pi bonds, so the two parallel pi bonds. So if we're looking at the parallel pi bonds, we cannot be using these px and py right there. So we're actually going to be using these ones. I think I said these ones here, but I actually meant these ones right here. So this E prime here is what's being used, are the possible uses for our parallel pi bonds, where this here and this here are the possible uses for our perpendicular pi bonds. But we're saying that the px and py cannot be used for our parallel pi bonds, and so we will be using our dx squared minus y squared and our dx for our parallel pi bonds. But anyway, so one last example here. So this is just looking at a molecule of the form AB6, which is an octahedral molecule, and so that looks like this. And so this is the octahedral molecule, so it has the 1, 2, 3, 4, 5, 6 atoms bound to the central atom, so the B sub 6 here. And so we get this reducible representation, which yields this right here after we go through the formula above to find out how many of these are in this right here. And so we end up with these bases, and we see that the T2U and the T1G, so the G being Gerada and the U being Ungerada, which is talking about whether they are symmetric or anti-symmetric to the inversion. So those ones don't have anything in them. And so we are just looking at the T2G and the T1U. So the 6 sigma bonds are the sp3d2 hybridized. And so the 3 px, py, pz orbitals are already utilized, and that means a molecule of the form AB6 can only have 3 pi bonds, because we are saying that these are out of the question here, because those are involved in the sigma bonds. And so the 2 d orbitals that are in our sp3d2 would be the dx squared minus y squared and the dz squared. And so these dxz, the dyz, and the dxy are going to be involved in our pi bonds. So this can only have up to 3 different double bonds on here. But anyway, like I said, this was somewhat of a crash course on hybridization, or I mean, I guess it's a little bit more than that. The general chemistry video that I have is more of the crash course on hybridization. This is looking at hybridization and how we can sort of bring symmetry into that. But in the next few videos after this one in this playlist, I will be actually getting into molecular orbital theory, which will be looking at those sort of energy diagrams, and eventually looking at how symmetry can be used for the linear combination of atomic orbitals and the linear combination of group orbitals and things like that. But anyway, I hope you found this video at least interesting, if not helpful, and I will see you in the next one.